Hello, and welcome to Lecture 8 on the topic of RC circuits. This is our final lecture of our group of lectures on the topic of electricity alone. Starting with Lecture 9, we're going to introduce magnetism and eventually incorporate electricity and magnetism together. But let's finish up this 8th lecture on the topic of electricity. So what is an RC circuit? Well, it's a resistor-capacitor circuit, so building on ideas that we've seen before. Let's take a look at our two objectives. We want to understand that a resistor-capacitor circuit, or resistor-capacitor circuits, are a type of direct current circuit that has non-constant current. Okay? We also want to learn that in an RC circuit, voltage can exponentially grow towards a fixed value or exponentially decay to zero, but current always exponentially decays to zero. Okay, we got to unpack that a little bit. Let's look at our two key terms. So RC circuit, you already know what I'm going to say, is that it's a circuit that contains a resistor and a capacitor and may include a voltage source. It would include a voltage source in the case of a charging capacitor. Okay? All RC circuits with voltage would be a direct current if not for the capacitor, since the capacitor causes the current to exponentially decay. Because as the capacitor fills, the current is impeded until the current eventually stops. We'll return to this idea a couple of times. RC circuits are not AC circuits. We'll discuss AC circuits in a later chapter. These are specifically oscillating circuits with sinusoidal behavior, and they are not RC circuits. We can have sinusoidally oscillating circuits that are AC circuits that do contain a capacitor, but we will return to those ideas later. The RC circuits we are talking about now are certainly not alternating circuits. But to be fair, they're not truly a DC circuit, although they are often simplified as one. Okay, so what is a time constant? Well, time constant is a term that's going to come up a lot. It's a term that's given to a particular set of variables for this resistor capacitor circuit. It's represented by the letter tau. It has units of time, so we'll take a look at that. So it's equal to RC. In a moment, after we go through our key equations and right before looking at some graphs, or actually after looking at some graphs, well, I'm going to show you this formula here. This is the time constant tau, it's the Greek letter tau, and we can see it's equal to resistance times capacitance, so RC, okay? I bring that up because I want to call attention to the units here, because the units of a resistor are ohms, and of course the units of capacitor are farads, okay? Now those are units that come up, but they're such highly derived units, it's easy to forget what they are. And I like that the time constant is equal to the product of those two very derived units because it has units of seconds. Let's see how. So it makes sense from Ohm's law that resistance is voltage divided by current, volts over amps. Okay, that's the definition of what resistance is. Meanwhile, capacitance is charge over volts. Okay, that's how we define capacitance. How much charge you can get for a particular voltage difference. Just like resistance is what voltage you get across for a particular current. Okay? Look what happens, the volts cancel out. So then we're going to have coulombs divided by amperes. Okay? Well, if we think about it, an ampere is a coulomb per second. An ampere is a coulomb per second. It is the definition of current. Current is charge per time, coulomb per second. Well, I have an ampere over here in the denominator, so of course that means I take the reciprocal of the definition of the ampere, and I end up with seconds over coulombs. And I still have a coulomb left over from my expression for capacitance in farads, again, which was just coulombs per volt. So as you can see, the coulombs cancel, and we're left with just the seconds. Indeed, the time constant, the product of ohms and farads, is just seconds. Really remarkable, and a wonderful connection of all these units and having that connection for all these units is so crucial for a deeper understanding of this topic. So let's say a little bit more about the time constant. It is the time it takes a capacitor to be about 37% charged, if you're charging it, okay? We'll see it also relates to how discharged it will be. In fact, it is the time for the charge to reach Q max, so that's maximum charge, divided by E, where E is the transcendental number that's equal to about 2.7. Kind of like pi is equal to about 3.14, that's E. Okay, we won't get into the history and mathematical meaning of E, but it certainly is relevant here. And you'll see we have a lot of exponentials with that same number, E, in the base of the exponential. Okay, and we'll take some natural logarithms as well. So it does come up in the math, but what I mean to not worry about E is we won't worry about the why E matters in the first place. We'll just get used to using it. But it's quite interesting, right, that we just have the maximum charge divided by about 2.7, and that's where we get the 37%. Because as a fraction, it's rounded to three significant figures, 0.368 of the maximum charge. And again, this is just charging the capacitor. I'll show you the numerical values of discharging the capacitor and the mathematical form in just a moment below, okay, including in graphs. So this idea of the time constant also applies to discharging a capacitor and also applies to voltage growth or decay and current decay, because after all, current always decays. All right, so let's take a look at our key formulas, all closely related. So our first one here is Q, little q, which is instantaneous charge. Instantaneous charge where? On the capacitor, because these circuits all have a resistor and a capacitor. So this is the instantaneous charge that's built up on the capacitor, okay? Q is the maximum charge in the capacitor. Q equals Q max, okay? That's when the capacitor is fully charged, okay? Now, obviously, a fully charged capacitor is dependent on the capacitance and voltage of the circuit. Well, the capacitance of the capacitor and then the voltage of the circuit, okay? And then look at this form here in the parentheses. Well, it's 1 minus e raised to the negative t over tau. T is the time, that's either a variable we're solving for or a value that we're given that we'll put into this formula. And then tau is the time constant. So notice that the power here of the exponential is, well, the units, I should say, are seconds over seconds, so it becomes dimensionless, which makes sense because everything in the parentheses also needs to be dimensionless, because after all, we need coulombs to equal coulombs on both sides of the equation. Another important thing to consider is just the form of this equation, because what does it mean for 1 minus e to the negative power to be a function? Well, if you think about e to the negative power, if we were to plug in t equals 0, what would this expression become? Well, if I had e to the negative 0 over tau, no matter what tau is, then I'm going to get 1. Because e to the 0 power is equal to 1, just like any number raised to the 0 power is equal to 1. And it doesn't matter that it's negative 0. It's still 0. Okay? And so that means that inside the parentheses, we'd have, 1 minus 1, which means we'd have 0, which means that the instantaneous charge at time 0, when you start the clock, is equal to maximum charge multiplied by 0, which is to say that Q beginning is just 0 coulombs. There is no charge at the beginning because you haven't started charging the capacitor yet. So of course that makes sense. Okay? This is what it looks like as a graph. What we have here, if we were to describe this function, is exponential approach to a horizontal asymptote, where the asymptote is Q, all right? Maximum charge, that is, big Q. Notice here that I've expressed a point along the horizontal axis, which is time measured in seconds, and where it corresponds to the variable Q, the dependent variable Q, the charging the capacitor, at the magical time of tau, the time constant, because I said that that corresponds to a capacitor being about 37% charged, okay? And if we look here, all right, we see that this is for a charging capacitor. So it takes for a capacitor to become 37% charged. This actually, yes, this actually is referring to a discharging capacitor, and we see it here in this expression as well, okay? And so I wasn't as clear about that as I wish I had been, because the graph, of course, is clear. The graph clarifies it for me as well, because I misspoke a moment ago when I said that this applies to the charging capacitor. This is a common expression, this 37%, and I think that's why I didn't give it a second thought, because a lot of times discharging capacitors are what we care about in physical situations. So this 37% is actually the time it takes a fully charged capacitor to discharge, or rather, in the time tau, this is the result of a discharging capacitor. Okay, I'll clear that up in the wording when I upload these notes, but please take note that here in the graph, I'm going to clarify what was a little ambiguous or downright incorrect a moment ago. So what do I mean? Well, at time tau, look where we are on the graph. We are at about 63%, okay? So for charging capacitors, after time tau has elapsed, however many seconds or fractions of a second that is, then the charge on the capacitor will be about 63% of maximally charged. And that's because this expression here is going to end up being is going to be 1 minus E, or it's going to end up looking like E minus 1 over E. Okay? This is the form that this equation takes. Okay? When T equals tau. And the reason we know that is because when T equals tau, we'd have an E to the negative tau over tau, okay? Which is just E to the negative 1, all right? So that means we'd be left with 1 minus 1 over E, okay? Then if I make that into have a common denominator, of course the common denominator is E, and then this expression here becomes exactly what you see on the axis over here, just simplifying it. Okay, so that's the idea. When the variable t equals the time constant tau, okay, for a charging capacitor, 63% charged after that much time has elapsed, okay? Also note that 63% and 37% complement each other in terms of equaling a either fully charged or fully discharged. That's no coincidence, of course, right? They sum up to 100%, okay? All right, and we'll see the 37% come up in the very next equation, so let's get to that. All right, so this is for a discharging capacitor, all the same variables, instantaneous charge, maximum charge, time constant, and so on, including the variable t. And look for a discharging capacitor. The capacitor starts with maximum charge. You see that if you just plug in tau, because you just have e to the negative 0 power, which is just 1. So then this whole expression just becomes 1, which means that little q equals big Q for time equals 0 seconds. All right, indeed, you start off at maximum charge. And after one time constant of elapsed time, you have 37% of your remaining charge, okay? Or you have 37% of the charge remaining, okay? All right, looks good. Let's look at the next two for voltage. Now notice what's going on with voltage. It's basically the same expressions. The only thing that's changed is the maximum, okay? But we have this exponential approach to a horizontal asymptote for the charging voltage, and we have exponential decay for discharging voltage, okay? All right, so let's take a look at the graphs for these. So here we have charging voltage. Voltage is reaching a maximum value, okay? And then we have discharging voltage. So how do we kind of interpret this in terms of the physical sense of the circuit? Well, what's happening as the capacitor is getting charged is it's building up a voltage to equal the voltage of the voltage source, the EMF, the battery. And once that capacitor is fully charged, say at some value of large T, much larger than tau, then the EMF, or I should really say the voltage across the capacitor, is exactly equal to the EMF. And in that case, the capacitor is opposing the voltage of the EMF, and the current has completely stopped flowing, which I'll reiterate in just a moment. But the point is that the voltage is growing across the capacitor, which of course makes sense because you think a capacitor has got positive charge on one plate, negative charge on the other. As you get more and more charge, as the charge grows to its final maximum value, you're going to get more and more voltage difference. Okay? Of course. Okay? And here is just the idea of discharging. In that case, as the charge is leaving, the voltage across the capacitor is exponentially decaying to 0. And finally, as promised, we have the current. And current is for charging and discharging, looks like this, okay? So no difference in the expression here. It's always going to have the same form. It's just going down to 0. And that's because when we're charging up the capacitor and it's building up its opposing voltage to the battery, that's eventually slowing the circuit down in terms of the current flow until the circuit is at rest and there's no more current flow. On the other hand, when you're discharging a capacitor, well, that makes sense because once there's no charge left on the capacitor, there's nothing to flow downhill. So the current has decayed to 0 in that case too. So quite interestingly, the current decays to 0 in all cases. In other words, for both charging and discharging. Okay? And here we have the time constant, tau, all right, just equal to RC, where R is the resistance and the C is the capacitance. Okay? Now I want to point out something very interesting about the I naught in this expression for the exponential decay of the current. Because although it's always true that I equals I naught times e to the negative t over tau, so the exponential decay, the expression I naught although we might just kind of take it for granted, isn't always as readily evident what it might be, especially considering that there are the two cases of charging and discharging. So I want to make special note here of what I naught is equal to in the two different cases respectively. Okay, zooming on this a bit. So I naught for charging equals the EMF of the battery divided by the resistance of the resistor, okay? Because these are, after all, our RC circuits. Because that makes sense. That's how much current initially is flowing into the capacitor before the capacitor builds up and opposes that voltage, okay? Stopping the current. All right, but on the other hand, if we think of a discharging capacitor, well, discharging capacitors almost are never connected to batteries. So it would make no sense to define the initial current of a discharging capacitor in terms of the EMF that doesn't exist. In that case, the initial current from the discharging capacitor is dependent on how much charge there is, usually a maximum charge, on the capacitor at the moment it begins the discharge. So here I naught is expressed as Q over RC, which we derive from the definitions of capacitance and Ohm's law. Okay? All right, so important thing to take note of. All right, let's finally get on to our examples. So we have three types of examples. Type 1, problems that involve finding voltage, current, and charge as a function of time for charging or discharging RC circuits with a single resistor and capacitor, like this one shown here in the picture. Okay? On the other hand, we have type 2, fairly complex problems that involve finding the voltage, current, and charge as a function of time for charging or discharging RC circuits with multiple resistors and capacitors. So there we'll have to find some equivalent resistance and or equivalent capacitance. Type 3, problems that involve finding energy as a function of time for a charging or discharging RC circuit. So there we're going to go back to the relationship of either power for a resistor or stored potential energy in a capacitor for a capacitor. Okay? And these may include single or multiple resistors or capacitors. All right, so let's take a look at a simple case, example 1. Now, it might look like there's more going on in the circuit than just a voltage source, a capacitor, and a resistor, but the other things shown in the circuit are simply a ammeter, because we're going to be talking about measuring current, so this would just be the physical device measuring it, the ammeter, and then a voltmeter, okay? Which both could be a multimeter. There's also a switch, okay? Many of these circuits do include a diagram that shows a switch because these circuits are transient. They don't work for very long. Once you either close or open the switch, the capacitor is either going to charge or discharge, and once it's done charging or discharging, you don't have an operating circuit anymore because there's no more current, right? Because the current always decays. That's the transient nature, the not very long lasting nature of all RC circuits. So we show the switch to imply that we can close it, measure the results during the time when the circuit's doing something before it stops doing something. Okay? And of course, you could then reset the switch to make it do something again. So in the circuit shown below, A, how much time does it take for the voltage to read 5 volts across the capacitor? So how would we tackle that? All right, so this is after closing the switch. This is a charging capacitor case because the capacitor starts uncharged. This is its capacitance, but it starts uncharged. Okay, here is the equation for the voltage across the capacitor that is charging. Remember, this is not the voltage from the battery. This is the voltage across the capacitor. All right, time dependent. This E is the EMF, the 10 volts of the battery. Okay, so here's the setup. What we're going to do is we're going to divide both sides by E, okay? And that's the step I show here, okay? That simplifies our equation. The expression inside the parentheses no longer needs to be in parentheses. Then we're going to subtract the exponential from both sides and subtract the ratio of voltages from both sides, okay? Because what am I doing here? Well, in part A, I was asked to find time. That means I'm solving for time algebraically. I need to isolate the variable t and solve for it, okay? So how do I go about doing that? Well, I take the natural log of both sides. I'm showing every step here. In future examples, I won't. If I take the natural log of both sides, these inverse functions will undo each other, and I'll just be left with the exponent, negative t over tau. Okay, it's very important that you have the negative because otherwise you're going to get a time that's negative if you were to say accidentally drop the negative, because the natural log of this expression will give you a negative because this ratio will always be less than E, 2.7. Okay, and then natural log of anything less than 2.7 is a negative value. Okay, so now let's go ahead and solve for the variable t. It's going to be negative tau times the natural log of 1 minus V over E. okay? V is stipulated at being 5 volts, the voltage across the capacitor. We know E to be 10 volts. We know tau to be RC, but we better calculate it, all right? So let's go ahead and find RC, okay? So RC is none other than the resistance of the resistor, the 2 ohms, times the capacitance of the capacitor in farads, and it's microfarads, so it's a millionth of a farad. Then times the natural log of 1 minus 5 volts over 10 volts, because the volts cancel. All right. And here I also take note that if we do multiply these numbers together, we get the time constant is 4 millionths of a second, or 4 microseconds. That's a very short time constant. That's actually kind of typical for small resistances and small resistors and capacitors like these, but we will see larger time constants as well. Okay? And so then if we actually solve for the time to get 5 volts, we end up with 2.8 times 10 to the negative 6, or 2.8 microseconds. Okay? Which, now let's think about that, right? Well, that's going to be, a little about 3/2 of 4, right? Because it's, this is close to 3 microseconds. Tau is 4 microseconds, okay? So does that kind of make sense in terms of how charged we'd expect it to get? Because we'd expect in one time constant in 4 microseconds, how charged should it be? About 63% charged. Well, and also then 63 to 63% as much voltage across it. Well, here we have 5 volts. Well, that's half the maximum voltage it can hold for this particular circuit. So in other words, the capacitor at this point is not quite 63% charged, it's 50% charged, because it's half the way there. And indeed, we see that this number is a little bit less than the time constant. So numerically, it makes sense, okay? In B, what is the current at this instant? Well, now we don't have to solve for T. We can simply plug T in. In this case, because we're charging capacitor, our initial current is the EMF divided by the resistance. And then we plug in all our respective values, 10 volts, 2 ohms. We plug in the time that we solved from part A. We plug in our time constant, okay? The 10 to the negative 6 cancel out, so we have a nice exponent that's just negative 2.8 divided by 4. And there's our value, 2.5 amps, okay? Looks good. Now, what percentage of the capacitor's maximum charge is stored at this instant? Okay, what do you think? I just said a couple times it's half the way there because it's got half as much voltage. 5 volts is half as much as it can have, because once it's fully charged, it's going to have 10 volts. That's when it stopped the current. It's opposed the current that the battery is trying to force. Okay, so we should expect then the percentage to be half, shouldn't we? Okay, so we'll go ahead and solve for Q max. It's just C times V. All right, so this is the capacitance that's given times the maximum voltage, okay? And then we'll consider the instantaneous charge at the particular time that we found, 2.8 microseconds. Notice here I've canceled out the units and the order, okay? So it is indeed, I just indeed wrote it as negative 2.8 divided by 4. And we get 1 times 10 to the negative 5 coulombs, okay? Well, how close is that to maximum? Well, we look here, right? Here, maximum amount of coulombs it can hold is 2 times 10 to the negative 6 coulombs. How do I know that? Well, a farad times a volt is none other than a coulomb, of course, right? So that means it's 50% charged, just like we'd expect, okay? Because it has 50% the voltage. All right, let's do a quick concept question before we do a few other practice problems. All right, so, and this is about the idea of kind of the initial and final states of a capacitor. Okay, so a 10-volt EMF battery is connected in series with the following 2 microfarad capacitor and a 2 ohm resistor. An ammeter and a switch initially open, a voltmeter is connected in parallel across the capacitor. At the instant shown, the switch is closed. What are the current capacitor voltage and capacitance charge values at the instant, the very instant when it's first closed? Okay, well, the initial current is just going to be 5 amps. Okay, that's just from Ohm's law. The initial voltage across the capacitor is 0 because it hasn't built up any capacitance yet. And we can see the initial charge in the capacitor is also 0 because no charge has had a chance to build up on the plates of the parallel plate capacitor yet. If there's no charge built up, there's no voltage across the capacitor. So when you first close the switch, at the very first instant, the capacitor is actually just acting like a wire, like an ideal zero resistance wire. Only once it starts to build up charge does it actually start to behave like a roadblock, eventually stopping the current until it opposes the current of the battery. And let's see that. So in B, after the switch has been closed for a relatively long time, so many times tau, maybe 10 times tau, right? So long enough that it's 99.9% fully charged. right? Because of course it's, it's exponentially approaching, it never quite reaches there, but it can get very, very close. What are the current capacitor voltage and capacitor charge values? Well, okay, once it's fully charged, there's no more current. The current has stopped flowing. The capacitor has caused it to stop. The voltage across the capacitor when it's fully charged is equal to the voltage of the battery. It's 10 volts. And the charge on the capacitor is the maximum charge it can hold, which is 20 microcoulombs for this particular circuit. Okay? All right, let's do another example. Okay, this is a pretty typical one. We have a switch that can switch between a position where it charges the capacitor and then switch down to a position where it discharges the capacitor. So it's kind of a handy dandy switch. See, when it's in position A, we have current flowing into the capacitor until it becomes fully charged or partially charged. Then we can switch it down to point B. At this point, the resistor and the capacitor are in a single loop without the battery, and that allows the capacitor to just discharge to the resistor. In terms of practically speaking energy conservation, the potential energy stored on the capacitor, the potential energy of the electric field, gets converted to heat energy via the resistor. Okay, so example 2. A RC circuit has a battery voltage of 31.5 volts, a single resistor of 12.9 kilo ohms, so 12.9 thousand ohms, and a single capacitor of 97 microfarads. If the switch is set at point A, for 755 milliseconds, and then switch to point B, then how much current will be flowing through the resistor after an additional 312 milliseconds? Okay, so in other words, we're going to charge the capacitor for 755 milliseconds, then we're going to discharge it for 312 milliseconds. That's what we're doing. So let's take a look. All right, so first, the capacitor is charged. All right, this will be the expression for charging a capacitor. Notice here, I've replaced Q max with capacitance and voltage of the battery. Makes sense, just these are my known values, okay? Again, that's just using the definition of capacitance, okay? And I'm gonna go ahead and find RC. It's a good idea to find this in one of your first steps. All right, in this case, RC is just gonna be my 12,900 ohms and my 97.1 microfarads. Okay, and that ends up giving me a time constant of about a third of a second, I guess, right? About 2.82 seconds, maybe closer to a quarter second. Okay, so now I'm ready to actually find my charge after the time of 755 milliseconds. Let's take a look. Okay, so this is just going to be CVB in front, okay, as shown here, and then in the parentheses, 1 minus e to the negative t over tau. Okay, well, t is just the time that's given, okay, and this is tau, right, RC. And we find then that the charge stored on the capacitor after that much elapsed time is 2.85 times 10 to the negative 3 seconds, okay? Excuse me, 2.85 times 10 to the negative 3 coulombs. That's how much charge there is on the capacitor. And I was just thinking about time because I was thinking, okay, well, the time that we're given, the 755 milliseconds, it's a few time constants, right? It's about 3 time constants. So we should expect this value to be pretty close to maximum charge, but not quite maximum charge. It's not quite fully charged when we switch the switch to position B. Okay, so then if we want to find the current flow after it's switched over to position B, we're going to take I naught times the exponential decay, and I naught in this case is going to be Q over RC. Notice that I chose Q as in lowercase q, not big Q, because it's how much charge is on the capacitor after that first 755 milliseconds. That's not Q max. Again, it's fairly close. I think it's like 95% the way there, but it's still not there. It's the instantaneous stored charge, not the maximum stored charge. Okay, all right. And that gives me a value of 10.1 milliamps, my initial current flow. All right, here I just go ahead and then plug in the values of Q and RC. RC I just put in because I already had calculated it before. And here I'll put in my elapsed time of 312 milliseconds, okay, because that is the additional time, or in other words, the time it discharges, the capacitor discharges, and I get 3.34 milliamps. This is good to think about because that means that we can really see that in this amount of time that it's gone down substantially. There's been a significant drop in the initial current flow has fallen off, okay, just as we expect. And how much charge will remain on the capacitor at this point? Well, the charge is decaying exactly like the current is decaying. I can go ahead and plug in my values, okay? Here, this is going to be Q naught, which is also just little q, okay? This is just the initial charge, okay? I guess I kind of wrote it this way so I wouldn't have a Q equals Q. So here I've just, for clarity, replaced the instantaneous charge with this variable called initial charge, okay? All right, but initial charge in this case would be exactly equal to this quantity, but again, you're gonna see that in the very next line, okay? It's the 2.85 millicoulombs of charge. All right, there's the additional time, okay? And there we go, we end up 9.41 times 10 to the negative 4 coulombs. Oh, I left my units off. I'll have to add those in. Notice also that the ratio between I and I naught and Q naught, well, they're exactly equal to each other because look, they've both exponentially decayed the same amount in those 312 milliseconds. So of course they would proportionally be the same. Okay, all right, let's move on to example 3. So the circuit shown has a EMF of 14 volts. The resistance of R1 is 14,000.6 ohms. And the resistance 2, this should say 2, is 22.2 kilo ohms, right? So 22.2 thousand ohms. And the capacitance is 38.9 millifarads. Okay, so 38.9 thousandths of a farad. Okay, which actually is a large capacitor, because notice most of the capacitors are in microfarads. If the switch is left closed for a very long time and then opened, what is the voltage drop across R1 after 0.44, not seconds, but 0.44 tau? What do I mean by that? Well, that means after a time that is 44% of tau. So after about half a time constant worth of time, okay? Following the opening of the switch, okay? All right, so let's work it out. Okay, so we're going to find the charge in the capacitor when fully charged. We know fully charged because we're told it was a very long time. Okay, so Q max is just going to be equal to C times EMF, okay, which then gives us 0.45 coulombs. A lot of charge in this capacitor. Okay, it's a big capacitor. Then, when the switch is open, the capacitor begins to discharge. Now, when it's going to discharge, it will discharge through both resistors, which means we need to find the equivalent resistance. Yeah, here's going to be the form of the exponentially decaying current. Tau is going to be R equivalent times capacitance. Since our two resistors are in series, R equivalent is simply the sum of R1 and R2. All right, and so when we plug everything in, then we end up finding a time constant of 1,430 seconds, a very long time constant. This is a type of capacitor that holds a charge for a while. Okay, so that means that the current after this much time, well, let's see, right? So here for I naught, I'm going to use the expression of Q over tau, all right? Or just Q over RC, okay, because that is equal to I naught. Again, refer to the first page. Okay, so that's what I have over here. And then just times the exponential decay term. Here, my variable t is 0.44 tau, which allows my expression for tau to just cancel out nicely, okay? So now I just have e to the negative 0.44, and then here I have pointed out what I naught is equal to, okay? And so then we end up with a current after that much time of 2.45 times 10 to the negative 4 amps, okay? All right, and thus the voltage difference across resistor 1, okay, because I said what is the voltage drop across resistor 1? Well, now that we know the current that's shared by both resistor 1 and resistor 2, we can find the specific voltage drop across resistor 1, delta V1, at this moment in time, because this is a time-dependent voltage drop, okay? But at this particular moment in time, it would be this time-dependent current times the fixed value of resistance for resistor 1, and we get a 3.58 voltage drop. We could likewise have found the voltage drop across R2, had we been asked for it. Notice we didn't end up using the actual value of tau, but I still kind of was curious to find out what it was. Okay? All right, on to the next one, okay? Let me clear that real fast. Okay, so example 4. Example 4, like the previous example, is all about finding the equivalent quantity. In this case, instead of having series resistors and finding the equivalent resistance of those two resistors in series, here we're going to have some capacitors in a more complex arrangement and find the equivalent capacitance of these 4 capacitors. Okay, and let's do that first. Okay, so we're going to consider what the time constant tau is. It's equal to RC, but in this case, it's R times the equivalent capacitance, the capacitor that could replace these 4. All right, and to replace these 4 capacitors, we use this expression here. I factored out the times 10 to the negative 6 because all the capacitors have values in microfarads, so they all share that. And notice what I've done. I've started with these 2 capacitors that are in series with each other. Well, when you add capacitors that are in series, you add the reciprocal of the sum of the reciprocals. That's this right here, okay? Then those 2 capacitors are in parallel with the 7 microfarad capacitor. Okay, so that means that these 3 collectively would be expressed like this. This would be the equivalent capacitance if we just had those three capacitors. However, we don't. We have a 4th and final capacitor, the 5 microfarad capacitor. Well, how do we add that in? Well, that capacitor would be in series with the equivalent capacitor that replaced the 10, 20, and 7 microfarad capacitors. And that means we do have to take the reciprocal of the sum of the reciprocals, which means that we take the reciprocal of the equivalent, which is this, and the reciprocal of the 5 itself, sum them together, and put them all under 1. And that, in totality, gives us the equivalent resistance of all 4. That last 5 certainly complicates things. Okay? All right, and that then gives us a time constant value of 1.83 times 10 to the negative 4 seconds. Small, but not as small as some. Okay? All right, so we'll continue on with the next step. I'm going to go ahead and find the initial current, which is just the EMF divided by the resistance because we are charging the capacitors, the arrangement of capacitors. So 125 volts divided by 50 ohms, so an initial current of 2.5 amps. Okay? And then we're going to go ahead and find the time until there's only 1.79 amps flowing out of the battery. Because initially there was 2.5, that number is going to fall off as our arrangement of capacitors becomes charged. Eventually, the voltage, of course, will approach 0, finally becoming 0. All right, but at some point, after not too much time, it will have gone from 2.5 to 1.79. Okay, so I'm going to do the same thing as I did in example 1, and I'm going to solve for t. Okay, so all I'm doing here is going through, isolating t by taking the natural log of both sides. I said I wouldn't show you, but I guess I do show you in this step. Okay, and here we finally have isolated the variable t. How long does it take? Okay, and okay, so we have it here. Notice that inside the natural log is just the ratio of the current flows, the final current flow over the initial current flow. Okay, and this is, of course, is just the time constant, RC. All right, and there we have 6.11 times 10 to the negative 5 seconds. All right, so it's definitely going to be not as much as the time constant, but that makes sense because we haven't got to a point where where we have reached 67% charged. Okay, so obviously it should be smaller than the time constant, consistent with our expectations. Okay, and that's about 1/3 of the time constant. Very good. All right, in part B, what is the maximum charge stored in this arrangement of capacitors? Well, that is as simple as multiplying the equivalent capacitance times the EMF. All right, this is once they're fully charged, once the current has decayed to 0, this would be the case. And we just have 3.66 times 10 to the negative 6 farads. All right, and multiplied by 125 volts. If you're wondering where this number comes from, that's just this part of this expression. If I just took this whole number here and divide by 50, I get this number, and of course the units becomes farads. All right, and there we go. Our maximum stored charge is 4.58 times 10 to the negative 4 coulombs. Okay, all right, let's do it again. All right, what we're going to do in this case is we're going to have equivalent capacitance, a simple case, just 2 parallel capacitors, equivalent resistance for 2 parallel resistors, and then we're going to talk about the stored charge on one particular capacitor, just like we mentioned the voltage drop across one particular resistor in example 3. So it's kind of a similar idea. As far as this goes, finding the stored charge on a particular capacitor and an arrangement of capacitors, there are really a limited number of problems we could see like this. If you are asked for the specific stored charge, on an individual capacitor in an RC circuit, it will almost always be, I should say always will be, a simple arrangement of capacitors, because otherwise it becomes impossible or very impractically difficult to calculate. All right, case in point, even up here in this example, finding the stored charge on these individual capacitors already becomes too difficult to easily calculate. Okay, but in this case, we can do it. Example 5. The circuit shown has an EMF of 145 volts. R1 is 4.06 kiloohms. R2 is 1.92 kiloohms. There, I correctly labeled it. All right. And capacitance 1 is 2.13 millifarads. Capacitance 2 is 75.5 millifarads. The capacitors are uncharged. Okay, so we're charging them while the switch is open. If the switch is closed, then how much charge will be stored on capacitor 2 after 2 seconds? Okay, so in this case, since we're given the time, we're not going to have to solve for the time. So no natural logs, just plug it into the exponentials. But let's work it out. All right, so this is a case of charging a capacitor. All right, and I say the capacitor because ultimately we're going to find the charge on C2, but both C1 and C2 are getting charged. All right, so my time constant is equivalent resistance times equivalent capacitance. Okay, and that's going to take the form of resistors in parallel and capacitors in parallel. Okay, plug in all my numbers, and I get 102 seconds. Okay, all right, well, we're only interested in 2 seconds, so it looks like we're going to have a tiny fraction of the time constant, okay? You know, about a 50th of the time constant, but enough where things have happened, okay? And the two capacitors will share the same time-dependent voltage that can be used to calculate individual charge, right? We know that from the very derivation of knowing that this is how we add capacitors in parallel. They share the same voltage, okay? We could also come up with that conclusion from Kirchhoff's laws or conservation of energy. However you want to consider it, they have to share the same voltage, okay? But it's important to take note of it. Okay, so here's the time-dependent voltage, okay? This is just the EMF of the battery. Okay, so there's 145 volts. Here is e to the negative t over tau. Our t is 2 seconds, our tau is 102 seconds. Okay, and so we end up with a voltage across either C2 or C1, a voltage of 2.84 volts. Okay, very good. And then we're going to find out how much charge is stored on capacitor 2 by multiplying its capacitance times the voltage that it shares with capacitor 1. All right, so then there is its capacitance as specified up here, 75.5 millifarads, and there is the voltage that we solved for. All right, and then we end up with a stored charge of 0.214 coulombs. Okay. All right, all set? All right, that's it. Very good. All right, let's do our final example, example 6. This is the only one that I decided to include that involves energy. But let's take a look at how that changes things a little bit, not too much. Okay. Also notice that we are going to have to think about equivalent capacitance because we have 3 capacitors all in series. All right, so in the circuit shown, each capacitor initially has a charge of magnitude 3.5 nanocoulombs on its plates. After the switch S is closed, what will be the current in the circuit at the instant that the capacitors have lost 80% of their initial stored energy? Okay, so here we have discharging capacitors. All right, I'm going to find the equivalent capacitance to replace these 3, right, using the formula for equivalent capacitance of capacitors in series, and we end up with 4.62 picofarads, because these are all very, very tiny capacitors. Pico is 10 to the negative 12, okay? So they are trillionths of a capacitor, well, a trillionth of a farad, whereas nano is a billionth, micro is a millionth, pico is a trillionth. Okay, all right, so then the time constant is just that equivalent capacitance times a garden variety resistor of 25 ohms, which gives us a tiny amount of time, right? Basically less than a billionth of a second, okay? All right, so let's think about the energy. Well, this is one of the 3 ways to express the potential energy stored in the capacitor, but this is a good choice because this is going to be dependent or in terms of the charge, which will be time dependent, divided by 2 times the capacitance, which is a physical quantity of the capacitors, and the equivalent capacitance, which we've already found. Okay, now we want to have 20% remaining because we've lost 80%. So I want this here, my final energy, because what I'm saying here, this is PE final, I want that to equal 20% of PE initial, okay? So I want the final state to be only 20% of the initial because I've lost 80%, and that's what I've written here, okay? I'm going to cancel out terms like the equivalent capacitance, and we'll solve for this final charge, then has to be root of 0.2 times the initial charge. Because see that, right? By saying that we have a certain percentage of energy means that the charge is going to change in a square root fashion because the energy is dependent on the square of the charge. Okay, so that's kind of neat. Okay, and so then the potential energy across the capacitor, or when the potential energy across the capacitor is 20% of the initial potential energy across the capacitor or within the capacitor. Okay, all right, so then in order to find the initial voltage, okay, all right, so what will be the current in the circuit the instant the capacitor is lost 80%, okay? So, we'll need the initial voltage to calculate the current. The initial voltage is the initial charge divided by the equivalent capacitance, so 758 volts, okay? That's the voltage difference across these capacitors. And in this case, that's the net voltage difference because they don't share the same voltage difference. Their voltage differences would sum up to this much, okay? And then the initial current is the initial voltage divided by the resistance, or 30.3 amps. Okay, the moment they start discharging, they initially are flowing out current at a rate of 30.3 amps. Okay, so then to find how much charge remains after this much time, okay, so from this expression, okay, then we can replace it with just root 0.2. Why is that? Well, because if I just take the ratio of the instantaneous stored charge divided by the initial stored charge, I already know that to be square root of 0.2. All right, so now I have this expression, the square root of 0.2 equals e to the negative t over tau. All right, and I'm going to solve for t. Okay, see what I'm doing here? Okay, now why am I solving for t? Because so I can plug it into my current expression. All right, not current as in the one that's happening right now, but current as in flow of charge. Okay, so anyway, so then let's find my value of time, and it ends up being 9.29 times 10 to the negative 11 seconds. Makes sense considering how small tau was. Okay, and now finally with that value of time, I'm going to plug that into current. Okay, all right, because I was asked for how much current is flowing at that point. So notice what I had to do. First of all, I had to find the mathematical relationship between stored energy and stored charge. Then I had to find some initial values. Then I had to find the time in order for this relationship to be true. And then finally, I'm using my exponential decay of current, collecting everything together to solve what was asked for. All right, so here's my initial charge, 30.3 amps, multiplied by e to the negative t, the time to get to 80% of lost energy, divided by my time constant. All right, and it's 13.6 amps. Wonderful. Okay, all right, so let's look at part B. So after the switch S is closed, what will be the current in the circuit at the instant that the resistor is outputting power at 20% of its maximum rate? Okay, well, let's think about that. So 20%, 80%, okay, but this is 20% of maximum, this is 80% lost. So this is actually saying the same thing, right? Because at the moment that I close the switch, the resistor would be outputting power at 100% of its maximum rate, because that's when the current is biggest. As the current decreases, so too does the power output of the resistor. And by the time that the capacitor has lost 80% of its stored energy, that should correspond with the resistor running at only 20%. So in other words, right, when this has lost 0% of its initial stored energy, then we'd have 100% of maximum power rate. Okay, all right, let me go ahead and show it mathematically. Okay, so here is the expression for the power output of a resistor, I squared times R. All right, and I want 20% of the initial power output to equal the current power output. Okay, all right, so in other words, that's going to give me a relationship between the instantaneous current, almost said the current, and the initial current, okay? And it's the square root of 0.2 relationship, just like we saw with charge. And if that's the case, then it's going to lead to this, just like before, just like we saw with charge. This is the exact same mathematical expression, right? Because after all, the charges cancel out in terms of their units. Likewise here, the currents are going to cancel out in terms of their units. So we're going to get the exact same relationship, just as with charge. And that tells us that the elapsed time and resulting instantaneous current must be the same. Okay, so indeed they do move together. And so the answer is the same answer we got for part A, 13.6 amps. And if we wanted to find, if we were curious, how much power is actually being outputted, we'd simply take that instantaneous value of current, multiply it by the resistance of the resistor, and we find out that it's 4,600 watts. Okay, All right, so I hope this lecture on these time-dependent RC circuits has been both interesting and informative. Thank you so much for watching.